In this video, we will review 3 different kinds of proportions in triangles and how to prove them and how to use them to find missing parts. The first one is the side splitter theorem. So your side splitter theorem says that if a line is parallel to a side of a triangle, then it divides the other sides proportionally. So that means that if you have this parallel line, so RS and XY, that this part of the side over that part, so it's splitting the side, has to be equal to this part over this part. So the proportion kind of sets itself up. So now we'll look at how to prove it. So we're starting out with triangle QXY, and it is RS and XY are parallel. So first is our given. And our first goal is to prove that we have similar triangles. So you have RQS, the smaller triangle, and then you have XQY, the bigger triangle. So one thing we know is that angle Q is congruent to angle Q by the reflexive property. And then since we have parallel lines, then I have a set of corresponding angles. So angle QRS is congruent to angle QXY because they're corresponding angles. That gives me enough to say that triangle QRS is similar to triangle QXY by angle-angle similarity. Now looking at, we want to prove XR is not a side of one of those triangles. So we're not going to want to use that right away. But RQ is a whole side. So we're going to leave RQ where it is. And then the same thing happens with YS. YS is not a whole side, but SQ is. So leaving SQ where it was supposed to be. So, looking at the two triangles, if this is my RQ side, then QX would have to be the corresponding side. So those two would have to go in the same ratio. And if this is QS, then QY would be the corresponding side. So that has to go in that part. So we know that because once you have similar triangles, then those triangles have to have proportional sides. So that's what we have so far. And I'm going to erase what's up at the top to make some more room. So right now, we have step 5, so now we're going up to step 6. We have proportional sides. So the bottom is what we want, RQ and SQ. That's in our proving statement. So that we're good with. But QX, we don't want to end with that. So we want to look and see maybe if we can write what QX is made up of. So this is QX. It's made up of QR plus XR. And then the same thing with QY. So QY, because this is QY, is made up of QS plus YS. So I know that because of segment addition. I'm going to take what I know qx is equal to and put it in place of qx down here. And then what I know qy is equal to and put it in place of qy. So let's erase to get more room. So that means that step 7 will look like qr plus xr over rq equals qs plus ys over sq. And we can do that because of substitution. So, what actually is going to happen here? If I separate the fractions, this is separate from step 8, just to show you the algebra behind it. Our fractions will look like qr over rq plus xr over rq has to equal qs over sq plus ys over sq. This fraction is the same thing on top and bottom as is this one. So it just becomes 1 plus xr over rq is equal to 1 plus ys over sq. So if you subtract 1 from both sides, then you're left with what you want to end with. So we're there. xr over rq has to equal ys over sq. So your reasoning for that, you could say division and subtraction, because that's what we did. We divide it and then we subtracted 1. And that's the proof for that theorem. So if we put some numbers with this, then we're looking at the sides getting split. So if it's on the same side, then it's going to go in the same fraction. So 3 over x plus 4 has to equal, and then what's across from the 3? X plus 2. And what's across from x plus 4 is 5. And then from there you can cross multiply. So you get 15 is equal to x plus 4 times x plus 2. 15 equals x squared plus 6x plus 8. So 0 equals x squared plus 6x minus 7, which can factor 2, x and x, plus 7 and minus 1. 7 times negative 1 is negative 7. 7 minus 1 is positive 6. So x equals negative 7 and positive 1. Looking at our picture, if I put negative 7 right here, then you would have that side length being negative 3, which does not work. So that means that negative 7 doesn't work. It's just x equals 1. Okay, so next we're going to look at a corollary. Corollary is just an extension of a theorem. So this is just an extension of the side splitter theorem. It says if 3 parallel lines intersect 2 transversals, then the segments are proportional. So instead of having 2 parallel segments within a triangle, we're just going to have 3 parallel lines. And then they get intersected by 2 transversals. And it's going to work the same way. We're splitting the sides. This part over that part has to equal this part over that part. Making sure that your segments are across from each other in the picture or across from each other in your proportion. So let's prove why this works. So we start out with the given. and we want to prove that the segments are proportional. AB over BC is equal to WX over XY. So we're going to start this by trying to have some triangles that we can prove are similar. Now there aren't any in the picture, but if I draw a line segment connecting W and C, or you could go from A to Y, that's going to create two sets of triangles. I'll have a set that goes from A, this is B, C, and this is W. We don't have a letter for this point, so let's just call it Z. Or you can make whatever you want. So we have those triangles, and we also have another set. WXY, Z, and then C. So, similar to what we just showed in the first one, because the lines are parallel, we're able to get some similar triangles. You have a reflexive angle at C and a reflexive angle at W. So angle C is congruent to angle C, and angle W is congruent to angle W, because they are reflexive. And then you can have some corresponding angles. You can have a set there. I'm going to put some numbers there. 1, 2, and then you can have a set of corresponding angles here and here. So I'm also going to put numbers there. 1, 2, 3, 4. Angle 1 is congruent to angle 2. Can't really see my 1 and 2. And angle 3 is congruent to angle 4, because they're corresponding angles. So that allows me to say that triangle CBZ is similar to triangle CAW, and also triangle WZX is similar to triangle WCY, and they're both by angle. So now, since I have similar triangles, I can use the side splitter theorem, which we just proved. So I can say that AB over BC would have to equal WZ, sorry, that should be on the same line, WZ over ZC, and also WX over XY would have to equal WZ over ZC. So the reason I picked those orders is because I have AB where I want it, I have BC where I want it, and I have WX and XY where I want them. So the reason that I know that is because of the side splitter theorem that we just talked about. Okay, so if you notice, these both have in common WZ over ZC. So that means if two different things are both equal to the same thing, then those two different things have to be equal to each other. So I'm going to erase some stuff up at the top to make some more room. So that means I can end with AB over BC equals WX over XY by the transitive property. Because two different things were both equal to the same thing, so then they're equal to each other. And then you're done. That's what you wanted to prove. And that's what you have. Okay, so let's look at some numbers. This is going to work the same way as side splitter. Part over part has to equal part over part. So 1 over x plus 3 has to equal x plus 2 over 2. Cross multiply. Making sure that you FOIL. And we should have that after you FOIL. Subtract 2 from both sides so that it's equal to 0. So factoring numbers that multiply to 4, add or subtract to 5, positive 4, positive 1. 1 times 4 is 4. 4 plus 1 is 5. So that means x equals negative 4 and negative 1. Does negative 4 work in this picture? If I plugged it in here, I would have negative 1. So negative 4 doesn't work. Does negative 1 work? Negative 1 still gives me positive side lengths. So x equals 1. Okay, so this is our last theorem that we're going to look at. This is called the triangle angle bisector theorem. And what this says is if you have an angle bisector in a triangle, then the side it intersects will be proportional to the other sides. So let's look at this in a picture. We have this angle that's being bisected because it has two congruent arcs in the two parts of the angles. So this line segment that is bisecting that angle is split into two parts, CD over DB, and they're going to go into the same fraction. So from the same side goes into the same fraction. And then CD connects with, let me erase so you can see all the letters. CD connects to only the side that is CA or AC, so that has to go across from it in the proportion. And then DB connects only with BA or AB, so that has to go across from it in the proportion. And then if you have numbers or a variable, you can cross multiply to figure out different side lengths. Okay, so let's prove why this works. So start out with your given. So we're trying to show that CD over DB has to equal AC over AB. To start, we're going to extend this line a little bit farther, and then we're going to draw another line that goes through it from B. And we're going to make that line parallel to AC. So now I want to look and see if I can get some similar triangles. I have a set of vertical angles here, so I'm going to put some numbers there. This is 1 and 2. So angle 1 is congruent to angle 2 because they're vertical. And then now using the parallel side that I just drew in, I have parallel lines. Now let's put a letter here in case we need it. Now a line that connects both of those parallel lines will be the one that goes from C to B, which gives me alternate interior angles. So if you would like to put some numbers there, call that angle 3 and 4. Angle 3 is congruent to angle 4 because they are alternate interior. So now I have two triangles that are similar. I have triangle ADC is similar to triangle EDB by angle. So those two triangles aren't going to give us quite what we want to prove because neither of them has side AB in it. So we're just going to do some extra things to try and get there. So using those parallel sides, this is A, C, E, B. A already has a single arc at it. A would be alternate interior to E, so we would note those angles are congruent also. So we've done 1, 2, 3, 4. Call them 5 and 6. So we know angle 5 is congruent to angle 6 because they're alternate interior. So, looking at our picture, I can put a single arc there now because that's what we just said. I have this triangle where it goes from A, B to E. Single arc, and now I have a single arc here. So that means that that triangle is isosceles, which would mean that those two sides would have to be congruent. So AB would have to be congruent to EB. You could say definition of isosceles, you could say base angles. So now let's look back at those triangles that we proved similar and look at what could be proportional. So I want to use CB in my final answer. Sorry, CD. So CD would be corresponding to CD goes from, in my picture, a triple arc to a double arc. So it'll have to be same thing from a triple to a double. So that would be DB. So I want AC where it is. I can use that because that's part of the triangles that I have similar. AC over, that goes from a triple to a single. So triple to single would be BE. So that's because of proportional sides. Now we're just about done because right here, BE, that is the only part that I don't want. But right up above, I said that AB is equal to EB, which is the same thing as BE. So I can substitute AB in for BE. And then that's it. You end it with what you wanted to prove. So let's look at some numbers. Our angle bisector theorem tells us if you have an angle that's bisected, that splits that line segment that's doing bisecting splits that side into two parts. And those two parts are going into the same fraction. And then x plus 1 touches the side that is 5, so that has to go across from it. And then 10 touches the side that is x minus 4. So that has to go across from it. Now you can cross multiply. FOIL. Subtract 50 so that it's equal to 0. And then see if you can factor. So you can factor that to x minus 9 and x plus 6. Negative 9 times positive 6 is negative 54. Negative 9 plus 6 is negative 3, which means x equals 9 and negative 6. Check your answers. If I put 9 in all of those places, the sides will be positive. But if I use negative 6, for example, here, then I get that side length to be negative 5, which doesn't work. So no negative 6. Final answer, x equals 9.